Hello. Because of some illness in my family, I'll be recording today's lecture at home and just sending you a link to it. So we're going to be doing Chapter 3, Section 1, which is over exponential equations. So the key to an exponential function is that the variable is the exponent. So what I mean by that is it looks something like this. We've got f of x equals 2 to the x. And to oversimplify things, we're going to see two basic kinds of exponential functions. We'll see exponential growth, where it shoots up to the right. And we will see exponential decay, where it falls off to the right. And both of those are really important functions to us. So we'll start by just looking at how to evaluate exponential functions. I'm going to kind of motivate for you a little bit here why we've got things like the rule about zero powers and negative powers. So what we're looking at is when we do x is 3, so we're trying to evaluate 3 to the third power. Now remember, that means 3 times 3 times 3. So that's going to be 27. Or 3 to the second power is 3 times 3, which is 9. Be careful. It's one of the number one mistakes that I see just in arithmetic. People writing things like 3 to the second equals 6. That is not true. Don't do that. Be careful. Okay, so 3 to the first power is just one of those 3's. And so you see there's kind of there's a definite pattern here. Every time we go down on this y column, we're dividing by 3. Which brings us to something really important, because we're going to do that same thing to get to the next step here. So 3 divided by 3 is going to give us 1. That's why 3 to the 0 power equals 1. We want that pattern to keep holding. Similarly, as we keep going down into the negatives, I want to be able to divide by 3 again. So what I'm saying is that I want 3 to the negative 1 to be 1 divided by 3, which is that rule we've got about flipping negative exponents. Okay? So 3 to the negative 2 is 1 over 3 squared, which is 1/9. Okay? So you can see this is an example of exponential growth. If we graphed this, it'll go through 0, 1, and then 1, 1, 2, 3, and then 2. It shoots way up to 9. On the left side, we've got negative 1 and 1/3, and then 1/9, and so it gets closer and closer to 0. Okay, so that's a growth. Okay, so we're just going to practice just evaluating some functions. So we've got f of x equals 5 to the x power, and we're wanting to calculate f of 3. This works just the same as when we do normal functions. So we're substituting in 3 for x, so 5 to the third power. That's 5 times 5 times 5, which is 125. Here's the trickier one, 5 to the negative second power for f of negative 2. We need to remember that that turns it into a fraction. We're dividing by that instead. So that's 1 over 5 squared, or 1 over 25. Now we're going to get into some really fun territory with fractions. Yay, everyone loves fractions, I know. So if we've got g of 2, that's 1/8 squared, which means 1/8 times 1/8. And remember, with fractions, you multiply straight across. So 1 times 1 is 1. 8 times 8 is 64. The other way you can think of that is we are distributing that exponent to both the numerator and the denominator. Okay, and this one I love, g of negative 2/3. So I'm going to do that down here. 1/8 to the negative 2/3 power. Now, if I want to make that power positive, I flip around my fraction. It's still to the positive 2/3 fraction now. Okay, and we can take this kind of in any order that we want. What this means is the cube root of, well, 8/1, so I'll just do 8 squared. Okay, so we can go ahead and let's go ahead and square 8. That's 64, and the cube root of 64 is 4. Okay, the other way we could have looked at that down here is I can take the cube root of 8 first and then square it. The order we do that in doesn't matter. It's both exponent operations. So the cube root of 8 is 2, and then square that and we still get 4. Okay, and now we're just going to throw a slight twist. So we're going to do two functions at once. So we want f of 0 minus h of 1. So let's look at f of 0 first. That'll be 5 to the 0 power. And then h of 1, so that's minus, and I'll use parentheses to help myself out here, 3 to the 1 minus 1 power, because I put in a 1 for the x there. Okay, well, 5 to the 0 power, anything to the 0 power, is 1. And then this is 3 to the 0 power, so that's another 1. So 1 minus 1 in the end here is 0. Okay, so now we're going to change gears a little bit. We are going to look at transformations with exponential functions. Hopefully you're feeling comfortable with that. What you're going to want to do is your parent function is actually defined by the base here. So you do need to graph that parent function so that you can really see what's going on. The good news is that the parent functions will always go through this common point 0, 1, because anything to the 0 power is 1. Okay, and then if I put in x is 1, y is 3, this is the same one we did out really slowly before. X is negative 1, y is 1/3. Okay, and so we've got this general shape without the little bump there. Okay, so we could make a whole separate table for g of x, or we can look at transformations. So there's two things happening here. There's that negative, which because it's in front of the x is going to be a y-axis reflection. Okay, and this plus 1, that's an outside of the function plus 1, so that's going to be a translation of up 1. Okay, so remember, we need to save those up and down transformations until the very last. So we'll start with just the y-axis reflection. The y-axis reflection. I'll do that in orange. So we're reflecting about the vertical axis, the y-axis. So anything on the left ends up over on the right, and anything on the right ends up over on the left. So we'll just move those 2 points that we graphed before and sketch this out. So 1, 3 ends up at negative 1, 3, and negative 1, 1/3 ends up at 1, 1/3, and 0, 1 stays where it was. So we've got this in between function here. Okay. And now we just need to shift that up 1. So each of my points, I move up 1. And I do want to kind of pay attention to this asymptote here. It's going to be at the 1 mark instead of at the x-axis. And that's our transformed function. Okay, this one's exciting. We've got 3/4 to the x power versus 4/3 to the x power, which if we rewrite the second one, it'll be a little more clear what's happening. So when I've got 3/4 to the x power, I do just need to sketch that out. Okay, and I will turn these into decimal form to make it a little more clear where we're graphing. Okay, so always x is 0, then y is 1. Anything to the 0 power is 1. If x is 1, then we've got 0.75 for y. If x is 2, then we've got 0.5625. So that shows us that on the right-hand side of the graph, we've got decay. This is decreasing. So it's something like this. Okay. So now we need to look at the left-hand side. So if x is -1, we can think about this 3/4 to the -1 power. Well, if I want to make that negative power into a positive, I flip the fraction. So that's 4/3 to the first power. So that's why this one is going to be around 1.3 repeating to graph it. So somewhere around there. -2, similarly, I could do 3/4 to the -2 power is really 4/3 to the +2 power. So that is going to be 1.7 repeating. So it's growing on that side, albeit fairly slowly, but it is growth. Okay, so overall this is decay because that's what happens to the right. Now, so at first it looks like this isn't the same as the parent function because it's got 4/3 instead of 3/4. But we've got to use that idea about using negative exponents to flip something. So if I want to make this look like it has the same parent function, I'm just going to flip around the fraction and make the exponent negative. So that tells me that it is a transformation of a y-axis reflection, which means we don't have to do a whole second table. We can just take each of our points and reflect them about the y-axis. So we've got something like this. And I know in my sketch that looks linear. It shouldn't. It is growth now. And this is kind of another really key point here. When we've got a number that is less than 1, well, between 0 and 1, like 3/4, that's going to be a decay function because the more we multiply it by itself, the smaller and smaller and smaller it's going to get. If we've got a number that's bigger than 1, then it is going to be a growth function because the more we multiply, the bigger the number is going to get. Okay, so here's another one that I would like you to try. You should really, seriously guys, pause your video, try graphing it, and see if your graph ends up like mine is. Okay, did you pause it? I really hope you paused it. You wanted to use the same parent function that we did before, so that would be 3 to the x as our parent. So that again was something like this. Okay, and then to actually graph f of x, we would just shift our parent function up 2. So that would be something like this. And our new horizontal asymptote's going to be at what? Y equals 2. Okay, this one I would like you to also try before I do it for everyone. So seriously, pause your video, try it out. We're totally going on the honor system. I hope you actually tried it. So we've got x and y. I'm going to just do the parent function first. So this is 4 to the x. So when x is -2, y is 1/16. When x is -1, y is 1/4. 0, 1, 1, 4, 2, 16. So this growth is much faster than our 3 to the x power was. So something like this. It shouldn't cross the x-axis there. Okay, now we've got to look at what all is happening here. We've got to take care of these things in the exponent first. So that -1 is actually a right 1. Okay, that is inside the exponent, so that's like the inside the parentheses weirdo opposites land. That negative in front of the x is still a y-axis reflection. And then after we've handled both of those, at the very end, we will move the whole thing down 4. Okay, so we want to move the whole thing right 1, so that's going to be here, 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 and here. Okay, I'm just going to do the dots for now. And then our y-axis reflection, so I'm moving everything from the right over to the left side, everything from the left over to the right side. So that's going to be like this. This 0, 1 stays put. Wait, no, it doesn't. Okay, let's see. This stays put, and then that. Okay, that was the y-axis reflection. And then the very last move is to move everything down 4. So 1, 2, 3, 4. Here. Here. And then even lower there. Okay. So it's going to look something like that. The black one is our final product. Okay, so the natural base E, someday I can tell you more about how it's derived, but for now just know that it's about 2.718. It is an irrational number, kind of like pi, that goes on forever and ever. And the crazy thing about it is it's really good at modeling things that happen in nature, like population growth or continuously compounding interest. It's just fantastic at figuring those things out if we use it as a base in an exponential function. So before we really start using E, we're going to look at some applications without it. You will want to have these in your notes as a reference. They are super, super important. So we've got doubling time. So anything that is doubling at all, we're using that 2 as a base to represent that. So we're multiplying by 2 again and again and again. P is the end result population, and then as it says there, PO is the initial value or population, T is how much time has occurred, and D is the doubling time. And then half-life, so that's basically the opposite of doubling time. It's something that's being cut in half. So like you hear half-life and you automatically think of like radioactivity, and that'll be a lot of our examples, but it doesn't have to be that. It can be anything just that's getting cut in half continuously. So A0 is the initial value, T is the time elapsed, and H is the half-life. Okay. My daughter must have gotten to this one. Okay, the current population of the island of Dune is 500,000, and the population is expected to double in 15 years. So we want to estimate the population in 5 years. Okay, so we will use the P version of the equation. P equals P naught 2 to the T over D. So in this case, right now our current population is 500,000, so that's our P naught. Okay, that 2 always stays there, so I'm just going to put times 2. And it doubles in 15 years, so that's actually our D, our doubling time. And we want to know the population in 5 years, so that's our T. Okay, so if I just evaluate this exponential, I will figure out that population. Now notice that 5 to the 15 power is really 1/3. And you will definitely need to figure out how to do this on a calculator. Well, no, I guess not. Wait, yes. 2 to the 1/3 power is the cube root of 2. And I don't really know anyone who can find that value in their head. So I'm doing 500,000 times 2 to the 1/3 power. You gotta find how your calculator does that. And I've got a population of around 620 29,961, which your book just rounds to 630,000 because, you know, close enough, right? And that is people in 5 years. Okay, so that's what we predict the population to be. All right, let's check out another one. So the radioactive isotope of potassium-42K used in the diagnosis of brain tumors has a half-life of 12.36 hours. So it's really important for them to know that half-life so they can know how much they would expect to see in the brain scans after a patient has ingested it in some way, or they've injected it or whatever. That's the kind of information they use in their diagnosis. So that half-life, again, is 12.36 hours. And we've got 500 milligrams potassium, and we want to know how many will remain after 1 week. So before we can do this, we've actually got a problem, because our half-life is given in hours, but we want to know how much is left after 1 week. So we've got to do a conversion here. And it's probably easiest to do weeks into hours. So I'll do 1 week is 7 days. And 1 day is 24 hours. I'm doing a little bit of old-fashioned dimensional analysis here. So it's very much like fractions. If it's on the top and the bottom, it divides out. So there goes the weeks, there goes the days. My ending unit will be hours. So 7 times 24, that's 168 hours that we're being asked to figure out here. So the equation we're going to use for this one is A equals A naught times 0.5 to the t divided by h, where h is the time it takes to half. That's our half-life. So we will do A equals 500 milligrams times 0.5 to the 168 over 12.36 power. Again, it's going to be so important to get friendly with your calculator here. 500 times 0.5 to the, okay, and then I've got around 0.040486 something, and that is milligrams of potassium. All right. So here is where E is going to come into play for us in this class anyways. We've got two kinds of interest equations. We've got compound interest, which is they can decide how long it takes for your interest to compound, which means they add your interest back into your account, and then you start earning interest on your interest. And some of those plans do it like every month or every week or something. So that's where that N, the number of times the interest is compounded, comes in. So A is the amount in the account after T years. N is the number of times interest is compounded. And R is the interest rate in decimal form, always in decimal form. Or there's the continuously compounded, which is we've got the amount in the account after T years, and R is the interest rate. Now, in both of these, P is your principal, which is the initial amount that you put into the account. Okay, so if we have $10,000 deposited in an account paying 4.5% compounding weekly, how much will be in the account in 3.5 years? So it does not see compounding continuously, so that means we use this equation, the P times 1 plus R over N to the NT. So we deposited the $10,000, so that's going to be our P. It says it's a 4.5% account, so that's 0.045 for R. Compounding weekly, so that N is the number of times it compounds in a year. So when we see weekly, we're going to go with 52 for 52 weeks in a year. And then N again on the outside, so that's 52, and then times 3.5 years. And then again, we just need to have a decent calculator and evaluate that. You should get something around $11,705.01. Okay, so you should try this out first. Pause and then come back. Did you do it? How was it? Okay, I hope you catch this. It said compounding continuously. So that means we're using the PERT equation. A equals P E to the RT. Now there should be like an E button on your calculator. Please don't just use 2.718. Actually use that E button. So this will look like 10,000 times E, still 0.045 times 3.5. Okay, sorry if you can hear my daughter there. And then it's around $11,705.81. Okay, so that is it. This is the assignment. This is still due next Thursday, even though we didn't physically have class. You still got a lecture. The homework's still due. If you've got any questions over any of this material, or if I made a stupid mistake, please let me know about it on Friday. I will be back then. And good luck to you. I'm also going to post a quiz over this material on Blackboard right underneath this video link. Do take that quiz for the same kind of participation credit that we always do. So that quiz is not optional. You definitely should do it just for participation credit. Okay. Thanks for listening, guys.